At this point, we spent a lot of time looking at the behavior of current-carrying wires placed in magnetic fields and also the magnetic field produced by current-carrying wires. One last time before we go on to our next object, let's look at the magnetic field produced by a wire and see if we can find the current. So at this figure on the right, we have shown for us that on the left side of the wire, the magnetic field produced by this wire is directed into the page. On the right side of the wire, the magnetic field produced by the wire is directed out of the page. What I'd like you to do is pause the video and using your right-hand rule for wires, determine the direction of the current in this wire. Is it directed up the page or down the page? Our right-hand rule for wires tells us that if we curl our fingers in the direction of the magnetic field, our thumb will then be directed in the direction of the current. So if we were to do that, where we point our fingers into the page on the left side of the wire and then wrap them around so they point out of the page on the right side of the wire, we find that the current that produced that magnetic field is directed down the page. Now let's suppose we were to take this wire and bend it so that it forms a loop like what's shown here to the left of example 2. In this case, we're given a loop of wire, and these X's represent the direction of the magnetic field in the inside part of our loop. And the question is, what's the direction of the current that created that magnetic field? And for us to answer that question, we need one more right-hand rule. The right-hand rule for loops is as follows. So, right-hand rule for loops says to point your right thumb in the direction of the magnetic field inside the loop. Inside the loop. If we were to do that, our thumb should be pointing towards the screen. And then, if we curl our fingers, they will then give us the direction of the current. So our fingers curl in the direction of the current. So pointing our thumb at the screen, curling our fingers, we find that for this loop of wire, the current, which creates a magnetic field pointing into the page on the inside, is clockwise. And remember, magnetic field exists in loops. So if the magnetic field produced by this wire is pointing into the page on the inside of the loop, it must also be pointing out of the page on the outside part of the loop. So that is our magnetic field outside the loop. If instead of just finding the direction of the magnetic field, we want to find the magnitude of it on axis of the loop, that is given by the equation down below. Where the magnetic field on the axis of a loop that has some radius r, and the point is some distance z away, is given by this equation, and the right-hand rule gives us the direction. This equation is not necessarily going to be very important for our class, but what is going to be important is this figure down here of two coils of wire separated by some distance r. These are called Helmholtz coils, and you'll see them in Lab 4 in a couple weeks. In Lab 4, we'll investigate the trajectory of charges moving in a magnetic field, and we'll use the Helmholtz coils to create that magnetic field. So what we'll need is to know what is the magnitude of the magnetic field directly in the center between those two coils. And so notice in the figure the two coils are separated by some distance r, and each one has a radius of r. And the point exactly in the middle would be a distance of r over 2 from each of the coils. If we want to know what's the magnetic field at that point, we'll need to find the net magnetic field, which is the vector sum of the magnetic field produced by the left coil plus the magnetic field produced by the right coil. Using the equation underlined above and evaluating it at C equals R over 2, we'd find that for the left coil, the magnetic field produced would be equal to mu naught I R squared all over 2 times the quantity R over 2 squared plus R squared, everything to the 3/2. And for the right coil, because it's the exact same distance away, and we're looking at magnitude now, the expression for the magnetic field is exactly the same. So mu naught I R squared all divided by 2 times the quantity of R over 2 squared plus R squared, quantity raised to the 3/2. If you were to do some algebra, what you'd find is that the magnitude of the net magnetic field inside the Helmholtz coils is equal to 4 divided by 5 raised to the 3/2 times mu naught I over R. And if we look at this picture, we see that there's not just one coil, but many of them. And if we assume that there's actually n coils in each of these loops, then we'll modify our equation that we just wrote down by just multiplying by n. So if there are n loops, then the magnetic field directly in the center of our Helmholtz coil is given by 4/5 to the 3/2 times mu naught n I all over R. I'll put a box around this so that we remember when we look at lab 4 and we're doing the pre-lab, we'll need this equation. And now for completeness, let's go ahead and answer number 3. So what is the magnetic field at the center of the loop? Again, we'll be using the equation underlined here. And at the center of the loop, so at the center of the loop, Z will be equal to 0. So knowing that fact, go ahead and pause the video and evaluate the above equation for when Z is equal to 0. Substituting in Z equals 0 and simplifying, we'd find that the magnitude of our magnetic field at the center of a single loop would simply be mu naught I divided by 2 times the radius of the loop. And again, if instead of just having one loop, we have n loops, so if there are n loops, then our equation for the magnetic field at the center becomes mu naught n I over R. And what I mean by n is that instead of just having a wire wrapped around to make one circle, we wrap it around n times to create n individual loops.